Okay, this is differentiation packet 42B, question 1. We're looking at related rates here. So we've got a ladder that is 13 feet long and it's leaning against the side of a building. The foot of the ladder is being pulled away from the building at a constant rate of 2 inches per second. So let's see. First step is to use a diagram. So here's my building. Here's my ladder. That's my ladder. And here's the ground. Okay, I know that the bottom of the ladder is moving at 2 inches per second. So if we call this the ground, right, let's say ground, G, then I know that the rate of the ground length or distance changes at 2 inches per second. Let's see, what else do I know? I know that the ladder is 13 feet. However, feet and inches, those are different units. I'm going to convert everything to inches since this 2 is in inches. So 13 feet long as a ladder, that's 156 inches. Okay, so that's going to be, let's call it ladder. Okay. I also know that my ladder is always going to be 13 feet. So if the ladder never changes, then we know the ladder is a constant. Unlike the length of the ground changes, right, depending on where the ladder is, and obviously the height against the building changes. But the ladder will always be 13 feet long, or 156 inches. It says, how fast is the angle formed by the ladder and the ground? So that would be this angle right in here. I'll call it theta. Theta is changing. Obviously, it's going to get smaller as the ladder goes out. How fast is that angle changing when the top of the ladder is 12 feet above the ground? So we need another variable for this side. Let's call it B for building. And I'm looking at when the building is 12 feet, that length, well, in inches, it's 144. What I want is how fast is the angle changing? So what I want is d theta dt. So I've identified some things that I know. I know that the ladder is 156 and that's constant. I know I'm looking at when the building is exactly 144, but the building is not constant, right? Because this height is changing. I'm calling the bottom the ground, and I know that dg dt is 2, and we're working all in inches here. So let's see, I've created a diagram. I've listed some of the facts that I know. I may need to find more facts before I can figure out exactly what's going on here. So since I've got some information here, I know that at the instant that the building is 144 inches, I know the ladder is always 13. I could find G, right? At that moment, how long is the G length? Well, that would just be a Pythagorean. I think it'd be 144 squared plus G squared equals 156 squared. And it turns out that G is 60. So at the moment that I care about, I know that G is 60. I could also find theta at the moment I care about. I could find theta a couple different ways, but we're looking at a SOHCAHTOA here, so you can either use sine, cosine, or tangent. I'll use cosine. So I know cosine theta equals adjacent over hypotenuse. So we'll inverse cosine that. And we want to stay in radians because it says radians here. So theta is 1.176 radians. Okay, so that's at the moment I care about. So I've listed a bunch of information. I've got all three sides of my triangle at the moment I care about it. I've got the theta. I've got dg dt, and I know that I want d theta dt. So now we need to figure out an equation that's going to work for us. Since I want d theta dt, I'm thinking some sort of trig, right? Pythagorean theorem is not going to help me find theta. An area formula will not help me find theta. So if I want to use theta, and I also know that this side is changing, right? And I know that this side is constant, and I like constant because I can use that number before I differentiate. So it looks to me, if I know the ground and I know the ladder and I care about the angle, I think I'm going to be using a cosine. right? Adjacent and hypotenuse. So the equation I'm going to use is cosine theta equals adjacent, which we're calling ground, over hypotenuse, which is a constant. It's the ladder length, so I can just create it as 156. So there's my equation. Step 4, differentiate with respect to t. Okay, so now I'm going to take the derivative. The derivative of cosine theta is negative sine theta d theta dt. It's bad writing. Let's see, g over 156, that's the same as a coefficient of 1 over 156. So the coefficient stays, and the derivative of g is dg dt. So let's now substitute and solve. Do I have what I need? Do I, and can I solve for what I want? I want d theta dt. So that's what I want here, which means I need to know a theta, which I know, and I need to know dg dt, which I know. So that's good. So I'm going to plug it in. Let's see, negative sine of, we said theta was 1.176 times the thing that I want, which is d theta dt, equals 1 over 156 times, where's my times? dg dt, which was 2. Okay. So let's see, that's 2 over 156, and then we're going to multiply over that sign. Sorry, we're going to divide over that sign, right? So then this is going to be times, that's a times sign, 1 over negative sine of 1.176 equals d theta dt. And we can kind of crank that out. And the final answer, once you do all of that, is negative 0.014. If we round to 3 decimal places, and that is in radians. And it makes sense that it's negative because we know that this angle is going to be getting smaller and smaller as the ladder moves out away from the building.